So this short video is going to be all about causality, because this is the big kicker when it comes to running a study, whether it's an experiment, a correlational study, an observational study, a field experiment, ethnography. This is the big question that we're asking ourselves is, can we actually say that my independent variable or my predictor caused a change in my outcome variable or my dependent variable? And causality is a very big decision-making factor when people are thinking about how to run their study. So causality means that your X variable or your predictor or your independent variable is actually causing a change in your outcome variable. So which type of study designs most allow us to do this? The answer here is going to be experimental. Because the reason that experiments have this ability is because everything is controlled for. The only thing that is changing between your different conditions is the thing that you're manipulating, as long as you're running your study correctly. And that is why experiments have the ability to do this. So causality, again, is the ability to say that one thing causes a change in another. And there are three criteria that must be met in order to determine, again, we're asking, does X cause a change in Y? And there's actually three criteria that must be met in order to say that X causes a change in Y. And yes, you have to meet all three of these. And it can't be a maybe, it must be that you are obviously, logically, and fully drawing each of these conclusions in your ability to say that X causes Y. So the first one is covariation. As X changes, does Y also change? What's interesting about this first criteria of causality is that actually all three study designs, and I know that I talked about four, I'm focusing primarily on experiments, quasi-experiments, and correlational studies right now. All three study designs, all three of these main study designs can actually meet this criteria. All three of them can, because in an experiment, you have maybe two groups. You have group 1 and group 2, and let's say that the average for group 1 is here. Forget about what's actually happening in those groups and what the outcome variable is, but let's say that the average for group 1 is here, the average for group 2 is there. As X changes, meaning that as you move from 1 to 2, is there a change in Y? Well, sure enough, it looks like there is. There's a difference in this between those two groups. And we talked about quasi-experiments. Statistically, quasi-experiments are the exact same as an experiment. It's just there's no random assignment in a quasi-experiment. And so again, it'd be the same type of thing. Is there a difference between your two groups? And we talked about how, group 1 might be smokers, group 2 is non-smokers. So let's put smokers here. Let's put non-smokers here. Is there a difference between the two groups? Sure enough, it looks like there's a difference between the two groups. Now, a correlational study means that as X increases, what's happening to Y? And again, you could have a positive relationship, you could have a negative relationship, you could have no relationship, but I want you to think about this. When the predictor changes, so does the outcome. Which of these graphs is the predictor changing and the outcome changing? This one is, this one is, this one is not. So as long as you have a significant correlation between your two variables, you've met this criteria. As long as you have a significant difference between these two conditions, whether it's an experiment or a quasi-experiment, you've met this criteria. So actually, almost every study design that's out there can meet this criteria of covariation. This is not a hard criteria to meet, but it's not just as one changes, so does the other. I mean, think about it. That's the sort of logic behind this, right? And I'm going to give you an example here. I need a volunteer. Typically, if this was in class, I would ask for a volunteer. And someone would come to the front of the room and I would say, okay, push me. And I wouldn't actually have them push me, but we would talk through this, right? So let's say that someone named Sally pushes me and I fall down. Well, the predictor changed. Sally pushed. That's a change in Sally's behavior, and I fell down. So, did Sally's push cause me to fall down? Well, we've at least met the criteria for covariation. Sally pushed, I fell down. There was a correlation between two variables. There was a difference between two or more conditions. Covariation just means that as your predictor changes, so does your outcome. Now, temporal precedence, on the other hand, I'm actually going to exit out here so that I can discard those annotations. Temporal precedence is asking the question, does your predictor come first? Does your predictor come first? So you've got two variables, you've got X and Y. And I want you to think about this from a logic-based standpoint. If Sally pushes me and I fall after Sally pushes me, would it maybe make sense that Sally's push caused me to fall? The answer is yes, right? If Sally pushes, then I fall. Makes sense that Sally's push may have caused me to fall. Now, there might be something else that causes me to fall, sure. But now let's flip it. Let's say that I fall and then Sally pushes me. Does it make any sense at that point to say that Sally's push caused me to fall? No. So let's talk about which types of study designs can meet this criteria. We already know that experiments, quasi-experiments, and correlational studies meet the criteria for covariation, because if there's a significant difference or if there's a significant correlation, we can meet the criteria for covariation. But temporal precedence is a little bit trickier, because in a correlational study and a quasi-experimental study, you're measuring the variables at the same time. So I might say, is extroversion correlated with the number of friends somebody has? Sure enough, they are correlated. More extroverted people or more outgoing people also tend to have more friends, right? That makes sense. Now, that being said, can we for certain say that extroversion came first and the number of friends came second? Well, we measured them at the same time, and as a result, the answer is actually no. Because it could be the case that, yes, higher extroversion causes people to go out and make more friends because they're more sociable, they're more outgoing. But let's flip it. Could it also make sense that having more friends causes someone to be more extroverted? Yes, it could. We could make an explanation for that. And so the issue with a correlational study is that because you measured those two variables at the same time point, you can't actually show that one causes a change in the other because there's no temporal precedent. You don't know which came first. Take as an example a quasi-experiment. Let's do the smokers and non-smokers and whether they have lung cancer or not. So we're trying to predict whether smokers are more likely to have cancer than non-smokers. Well, we measure it at the same time. We say, are you a smoker or not? We place people into groups. That's a quasi-experiment. We're not randomly assigning them, though, because we can't randomly assign someone to smoke or not. We just measure it. They come into our study, we measure it, and we test it, right? It doesn't mean that a quasi-experiment is garbage, but now think about this. Do we know for certain that they smoked before they had lung cancer? No, there's a number of other things that could cause someone to have lung cancer or could result in someone having lung cancer. So as a result, if I run a quasi-experiment, because I'm not randomly assigning people to condition and I'm not for sure doing that manipulation before, I'm not manipulating whether they smoke or not and then measuring lung cancer. I'm measuring them at the same time, and I just don't know for certain that one came before the other. Now, why does an experiment meet this criteria? Let's actually draw this up. So in an experimental study, participants, I'm going to draw a timeline. Here. Participants enter the study. They are then randomly assigned to group A or group B. Then they undergo the manipulation. And then, so here's when, like, this is the manipulation. The manipulation happens here and here. And then we measure the outcome. So we randomly assign people to one of two groups. Maybe it's drug versus placebo. And then we measure their health at the end. So we're seeing, does this new drug significantly improve people's health outcomes? Well, do we know for certain that the manipulation came before our measurement of health? Yes, just from a logic standpoint, we did this first and we did this second, and there's no other differences between these two conditions because we randomly assigned people to the conditions. We washed out all of the differences that people came into the study having by randomly assigning them to condition. So have we definitively shown that the manipulation came before the outcome? The answer is yes. So in an experiment, so actually all three, so experiments, quasi-experiments, correlation studies, all check this box. But the only one that can for sure check this box of temporal precedence is experiments. The last one is internal validity. What this is asking is if you have the ability to rule out third variables or confounds. So there's a very popular study or a description that higher number of ice cream sales seem to be correlated with the number of shark attacks in a given setting. And this is actually a real correlation. As ice cream sales increase, the number of shark attacks also goes up. This is a positive correlation. But does ice cream sales lead to shark attacks? No, it doesn't even make sense. The third variable or the confound here is temperature. That people tend to buy more ice cream when it's hotter outside. They also tend to swim in the ocean more when it is hot outside. And as a result, temperature is actually the thing that is causing both of these to increase. And as a result, these two things are just accidentally correlated, but it's actually this that's causing both of those outcomes. And so with internal validity, we're asking, do we have the ability to rule out third variables or confounds? Well, the only thing that can really rule out third variables is random assignment. That's the only thing that can rule out third variables, because these are those other things that could be influencing. And think about it. What is it about random assignment that rules this out? Well, by randomly assigning people into groups. Again, you assume that there are some people that are more intelligent than others. There are some people that are more liberal than others. There are some people that have higher GPAs than others, that are more extroverted than others, that are more open, more neurotic, more anxious, study harder, so on and so forth than others. But by randomly assigning them to condition, you hopefully wash out those differences, and as a result, you can actually rule out third variables and confounds. So the question is, which study design is the only one that randomly assigns people to condition? You've guessed it, experiments. So when it comes to causality, experiments, you can see here, experiments have met this criteria, have met this criteria, and have met this criteria. And actually, they are the only type of study designs that can for sure imply and draw conclusions of causality.